Right. Good morning, everyone. So I hope also that you had a great weekend. I had an awesome weekend. So I'd like to talk about machine learning, actually not for task fMRI. I forgot to update my slides. I'd like to talk about machine learning for fMRI. And it's going to be a bit of a lot of slides, actually, because I'd like to get concepts through. And we'll do 2 sessions of notebooks, works on notebooks. The code is done with Nilearn. If you've never used Nilearn yet, that's a good moment to get started. And so in terms of slides, in terms of concepts, I'll first do a session on task fMRI. That's going to be before the break. And I'll cover encoding model and decoding models, and I'll explain what it means. And then after the break, I'll discuss rest fMRI. And for the first session, I'll be interested in task fMRI and with a specific focus on cognitive neuroscience. So basically linking psychology and neuroscience, so the neural implementations. And so really the idea is, how can you understand mental processes, mental operations by looking at brain activity? And for this, I'll be using machine learning. And for me, it's a profound tool. It's something that is the future, not of everything, but in many places. And just to set the notions, what I call machine learning is basically statistics, but used for prediction, so focused on out-of-sample properties. I'll come back to this. And what we find is that there's a lot of computer science to it. It's not just pen and paper statistics. And so what we're seeing is that as we're getting richer and richer data, there's a paradigm shift from standard statistics to machine learning. And the reason that this is the case is that richer data means that we have higher dimensionality. By higher dimensionality, I mean that the objects that we're manipulating are more complex, and I'll come back to this. So this is great because it means that it enables richer model, but we can't just use our standard approaches to statistics on this. The good news is that my vision is that as we start understanding how to use machine learning to answer questions we're interested in, we can make these questions a bit more open-ended. And the reason technically that we can do this is that machine learning can tackle a large number of features. So you've been through the machine learning course with Jake, so I suspect that the notion of features, of samples are familiar to you. Is that the case? Yeah. Okay. So really the difference I'll make between machine learning and standard statistics is that standard statistics, for good reasons, will break down when you have a large number of features. It works well when you have a small number of features, whereas the methodology of machine learning can be applied with a large number of features. And from a scientific perspective, this allows us to tackle more open questions, okay? But when we do this, there's something that we need to do, is to shift from testing the value of parameters to using prediction as a tool for scientific inference, okay? That's an important point. And the delta that there is between the machine learning literature and this course is that we find that in brain sciences, people are interested in understanding the brain, not predicting, even though the term understanding is a very open one and a very cultural one. So, but the thing is, we need to reformulate prediction problems in a way that map to knowledge of the brain. And so the way I think about this is that if we're looking at cognitive neuroimaging, we have on the one hand measurements of brain activity, and on the other hand some description of behavior or pathology. And from a machine learning standpoint, what we're going to try to do is to learn brain-mind associations with machine learning. The benefit is that they can explicitly generalize, okay? When the goal of science is to generalize beyond the data that we've observed, but this generalization is usually conceptual. It's usually implicit. Machine learning is geared towards generalization. So all these associations between the brain and the mind, we can test to see if they generalize. And so for instance, we can be interested in looking at brain images and concluding on what this tells us on the behavior or the pathology. So this could be for interpretation purposes of these brain images or for diagnosis purposes. We could be looking at the opposite problem, which is what can I predict about brain features given description of behavior or of pathology, okay? What this can inform us is how do I need to decompose behavior in relevant aspects for a good description of the brain. We could be interested in unsupervised analysis, so I think Jake has mentioned a bit unsupervised analysis directly on brain data. And if we do this, we're going to be looking at things like resting state. And the reason this is useful is, well, there are many reasons, but one of them is that it's much easier to get data without controlling the behavior, data without labels, basically. And that's a common thing in machine learning. Data without labels is easier to get than data with labels. So in general, unsupervised learning is less powerful than supervised learning. The power of label in machine learning is a very strong one, but labels are hard to get. And something that I won't cover, but that's also interesting, is that we could be looking at machine learning directly on descriptions of behavior or pathology. And this can be interesting to extract representation of the behavior or to capture, say, semantics across the different terms that might be used to describe the behavior. So the latter has nothing to do with brain images, but I think it's very important. Okay, so this is just a small schema of where we could be using machine learning, and I'll be talking about the different steps. And I'll start with encoding models. So what encoding models do is that they predict brain responses from stimuli. That is overall the definition of an encoding model. So the methodology of encoding is that you specify a model of brain responses in a way that is left to the researcher. And this model is then tuned on brain activity. So it's adapted to explain well brain activity. And that's the fitting or the training part of machine learning. And once we've done this, it's very important that we test it on left out data. The reason this is important is that the minute we've adapted choices in our model to explain best the data, the minute we've done this, we can't control what it means that the model explains well as the data. Because a more flexible model will, by construction, explain better the data because we have more parameters to tune, okay? So this is a standard problem of machine learning. It's known as overfit, for instance, and the standard solution is to test on left out data. But I'd like to say that it's also a scientific problem that once you're starting to tune your model, your hypothesis to the data, then you can no longer control whether this model or those hypotheses are valid, and you need new data to test it, okay? So I don't see such an opposition between the machine learning process and the scientific process. And so often I'm told that machine learning is there to predict and science is there to understand, there's not such a clear opposition in my point of view. So really what encoding models are going to do is that they're going to specify some form of model, and then they're going to cross-validate on brain activity to see if the model explains well brain activity. Okay? And when we think of it, it's not completely different from the standard analysis in fMRI. So standard analysis in fMRI uses sets of stimuli that are modeled, so the brain response to a set of stimuli is modeled. So you're going to present stimuli to patients, and you're going to get activation maps using some simple linear model to do this. And this linear model is a model that explains brain activity as a function of the stimuli, right? The only difference with the standard analysis is that we're not testing out of sample, we're using standard test statistics. And because we're in simple linear models, we're controlling for the complexity of the model using things like the coefficient of determination of the design matrix rather than cross-validation, okay? So there's no opposition between encoding and standard analysis. We could see encoding as a generalization of standard analysis, or standard analysis as a subset of decoding. And the real difference is that encoding will allow us to tackle design matrices or models that explain the data that are much more complex. And now I want to illustrate why this is important from an inference standpoint in cognitive neuroimaging. And I'll take the specific case, the visual system. That's one of the systems that's best understood in the human brain. And so if we take a step back and we look at the history of understanding the system, there's an important moment, which is when Hubel and Wiesel did experiments that revealed the functional property of the primary visual cortex of V1, that is a region that responds to edges. And the way they did this is that they did experiments where they moved basically a line of light in the visual fields of cats, and they recorded the response. And they could show that there was a very clear response, very specific response to this line. So when we think about what happened here, they crafted a stimuli that was well adapted to the function of the region that they were studying, and then they looked at the response of the region. And then people kept going on this paradigm and pushed it much further and crafted many different stimuli that were adapted to many different parts of the visual cortex. And this line of work has basically led us to our current view of the visual cortex, that it's basically a cascade of regions that are tuned to specific aspects of the stimuli. But the way this was done was by crafting stimuli to explain well brain activity. So in a way, this was done with informal encoding procedures. All right? So based on this, we can formulate hypotheses. Is there a face region? Is there a foot region? Is there a left big toe region? So that's good. We have hypotheses, we can test them. So we can acquire data with an opposition from face to left big toe, and so we're going to acquire data, lots of data, and we're going to do a standard analysis and a contrast. And if we have enough data, we're probably going to get a difference. And so we can publish evidence for the left big toe region in the brain. Hopefully we'll get a high impact factor journal, and that's good, right? Maybe it won't get through, unfortunately. Why not? Well, the reason it won't get through, I've tried getting people to accept my hypothesis, but it didn't work. And the reason it won't get through is that people don't believe me that there's a left pictorial region, and so they don't believe in my experiment. And they tell me, okay, maybe your data is going to show this, but it's meaningless. And if we take a step back, really the core region there is that brain mapping must rely on, so brain mapping uses cognitive subtraction. What I just showed you, the supposition is the idea that you can decompose the stimuli or the task in a set of subtasks that are relevant, okay? And so if your decomposition is stupid, your analysis can still run. You'll still, crunch data, but you've started from a meaningless decomposition. But then I find this a bit problematic because basically we need a good decomposition to use brain mapping, and it's pretty much the case. So really the core aspect here is that brain mapping can only test a theory of the mind in its own paradigm. You need to accept the theory of the mind. You need to accept the decomposition of mental processes to interpret the results of functional task fMRI experiment. Okay? And so what I'd like to show you is that encoding in a formal way can at least relax a bit this. And the reason is that you can start decomposing mental processes on many different possible decompositions because encoding can tackle more complex models. All right? And so people have been doing this for a little while. People like Jack Gallant and others have been doing this for a little while. So how do we decompose visual stimuli? So the hypothesis that the low-level visual cortex is tuned to edges, there's a hypothesis that tells us that it's probably tuned to edges because those edges are really the simplest way we can describe natural images. And any kind of analysis, statistical analysis on natural images will reveal basically Gabor filters. So Gabor filters are basically edge detectors. And you can do this in many different ways. So basically the natural simple statistic of natural images is Gabor edges. They give a good representation of natural images. So how do we do a model that captures a bit richer description of natural images? So well, we can use what's very trendy these days, which is deep convolutional networks. And why might we want to use deep convolutional networks? Because they're a mathematical model that works extremely well on extracting information from natural images. Okay? They're a state-of-the-art computer vision. They're a mathematical tool that really solves the problem of understanding natural images. Okay? So what they really give us is a hierarchy of different representations from Gabor filters. So that's the input images. So here we have simple filters, and as we move forward we have more and more complex filters. And what's important is that those filters are driven by the statistics of the stimuli we put in. So if we are going to extend the hypothesis of Olhausen and Field, that the visual cortex is tuned to statistics of natural images, given that the convolutional neural nets are also tuned to statistics of natural images, then they give us representation that makes sense to study the brain. Okay? So then we can do an encoding experiment. And we can take data where subjects have looked at images. We can use a convolutional neural net to extract the intermediate representations that correspond to these images. Okay? So the ones that I show you here. So for each stimuli, we transform it with the convolutional neural net, and we get a hierarchy of representation. The first one being basically the Gabor transform of the image, and as we go further, we get more and more abstract representations. And then we can see how these representations explain the brain activity, okay? So basically, we've transformed our stimuli in a vectorial representation, and then we can use a simple predictive model to go from this to the brain activity. So when we do this, there is a trick, is that those convolutional neural networks, they require a huge amount of data, a really huge amount of data. The good news is that we can train them without brain activity, because they're just a model of the stimuli. So we can use, the easiest way to do this is to use pre-trained models that have been trained on extremely large volumes of natural images. Once we have them, we can use them to transform a smaller number of images that we've shown to a subject and for which we have the brain response, okay? And the reason is it's very hard to get extremely large amount of data with brain response. And now that we have this, we have two things. We have brain activity, we have a description of the stimuli, and we can start learning a predictive model between the two. And then what we do is that we use a very simple predictive model. We use a linear regressor, so like a ridge regression. The reason we do this is that we have, a few thousand images in terms of response to stimuli, and the inner descriptions of the stimuli that are given by the convolutional neural net are high dimension. The convolutional neural net really creates many different descriptors that describe the image. So we have a high dimensional problem, and we can only use a simple machine learning tool to tackle this high dimensional problem. And this we're going to do in a cross-validation loop just to check that our model is fitting the data well. Okay? So different people have done this. Yeah.
Can I sort of,
sure.
So you can draw this picture. This is the optimistic view, but the pessimistic view is that at every step of the way there are things that are different between the convolutional net and the way it does it.
Yeah.
So there's no biophysical mechanism that implements back propagation, for example. Right?
Oh, that I'll challenge. This is something that I hear a lot, and I find it's just meaningless, and it's said by, there is, I mean, when your kid learn, there is tuning, and this is adaptation of the weights. But anyhow, go on.
The mechanism itself of learning is not, and also, okay, so, that.
Sure, you have silicon, you have biology.
The activation functions that we use in convolutional networks.
Sure, whatever.
Are not the activation functions that are used in
I'm not saying that the neural net is a model of the brain. Well, why not actually? It's not, it's less crude model than most of the models that people put out. Drift diffusion is, so people use, I hear a lot of this, and then I hear people using models that are ridiculously crude, and they're fine with this. A model is a model, it's not the real thing. But anyhow, I'm not claiming that we have a convolutional neural net in our brain. I'm claiming that they extract similar information. And that's a very different claim, right? But that said, I find that a lot of the critique that are done to this alley of research, because it's been instantiated in many places, I find it slightly dishonest, because people have been doing horrible models that are absolutely meaningless and finding post hoc explanations of them. And
saying this is a bad model, but it's not.
But all the models we're using are bad. So when we started this area of research, we didn't start by convolutional neural nets. We started with the H-max models and all these. They don't explain variance at the brain level. They just don't. And when you look at them, you'll find that there's a ridiculous amount of arbitrary choices, and that when you look at the different papers published by the authors, and in each paper, these arbitrary choices are different. So you can't even, publish saying, H-max doesn't work well. Or actually, this is what Jim DiCarlo did in this paper. He showed that convolutional neural nets worked better than a set of classic models for vision, but this is challenging because you need to test a lot of things to really show this. But from a high-level perspective, those models that, and they're kind of fading away, which is a good thing. Those models, those conceptual models that people are putting forward, when they have data, they start making all kind of choices that may or may not seem important, but that change a lot the way the model explains the data. And those choices, honestly, are not driven by biology. They're driven by the need to fit the data, except it's not done in an explicit way. It's done by gradient student descent instead of gradient descent. And so there's no way we're controlling for overfit there. And this overfit does happen. So what I'm saying is this is a model. This is not a biophysical model, but at least its complexity is controlled. Do I answer your question? We're not the first one to have done this, right? I mean, my favorite paper is, I realized my cursor is not on this screen, so I've been pointing to things and you've not been seeing them. My favorite paper is the Yamins paper by the Jim DiCarlo group, where they worked on recordings of electrophysiological recording of IT, and they showed, so this is very fine data, and they showed that they could explain this data much better than using the conceptual models. Okay? So this is an example of an encoding model, of encoding models, and I think they've been fairly successful to study the visual cortex. And let me show you one result that we got with them, because we were excited when we saw that. This is real data. This is data, by the way, that was acquired by Jack Gallant, so we should really thank Jack for sharing his data. He hates sharing his data, but he feels he must do it, so he does it. That's true. And he does it, he really does it. Like, it's not like he doesn't give the data, he gives the data. So, and it's beautiful data, it's really, really beautiful data. So what we're showing here is through the different levels of the neural net. From the bottom is the simplest level, the first level, which is basically a Gabor transform of the image, and as we go up the hierarchy, we're color coding the level that explains best the brain activity, okay? So what we're seeing here is that the low-level models, the low-level layers, explain better the low-level brain areas. And as we go up, we can see that the high-level layers explain better the high-level brain areas. Okay, so what we're doing when we're doing this is that we're doing brain mapping of functional areas without having really specified a priori what these functional areas were doing. We're just, Cedric?
Quick question. Do you have a notion of how the convolutional network size changes this one?
The question was, do we have the notion of how the convolutional size changes this mapping? My answer is no. This was done, it was only published in 2017, but this was actually fairly, the hard work was done fairly early on, and the tools for neural networks, for convnets, were not as good, and we were completely struggling. This is the most irreproducible study I have. It's just, we still have 13 terabytes of dump of intermediate results on our disks, because we think maybe one day we'll be able to reproduce, but the technology that underlie these neural nets has completely changed. And you can probably still download the old things, but they'll probably not work on the new hardware. I mean, it's a nightmare. So my answer is no. I would hope not much, because we didn't tune. I mean, we knew we had a result because one day this image popped up on our screen. Like, I was like, can we plot the layer that explains best the data? And this just popped up without any tuning or anything. And then I was like, wow, it's really in the data. So I suspect it's reasonably robust, but the specific details, like this voxel, is it in green or in yellow? Nah. And conceptually, it will generalize. This tells us we should look at generalization.
I think the question was a little bit follow-up on Ariel's question earlier, that we know a lot about the visual system, including the fact that retinal neural networks do a lot of computation before you even get to particle levels. And so I think this notion of how a model maps onto the biophysics of the system, I think is still a very open question. And to say something explains how the visual system works, I think it's stretching it a little too much.
Well, I disagree there because we're really finding reasonably good mapping between representation. So I think maybe the disagreement is on what explains mean. I think we have a weak explanation. We don't have a mechanistic explanation. You know, that clearly we don't have a mechanistic explanation. It would be, and there is interesting, work looking at, can we get, some form of mechanistic link between things that happen in the brain and things that happen in neural nets, but it's it's clearly going to be using completely different neural nets, okay? We're probably going to have to look at things that are Bayesian deep learning, because the kind of mechanisms, the kind of perturbations that happen are much more similar. But in terms of representation, I'm reasonably convinced that there is a link, just a link, between the representations that the neural net captures at different hierarchies and the representations of the brain. Doesn't mean they're the same representations, by the way. We couldn't claim this, it'd be wrong, but it means that they capture the same information. So in terms of decomposing the stimuli in relevant information, I think this maybe doesn't solve the problem, but at least addresses it well. In terms of mechanism, completely agreed. But my point here is this avoids making strong hypotheses on the decomposition of the stimuli. And my point here is not, we've solved vision, let's move forward. Okay? And really the reason that we can do this in vision is because it's much easier to get pre-trained neural nets that work well, and because it's much easier to get a lot of fMRI data because visual stimuli are the easiest to study. And people have started showing this in different places. Language, for instance, there's starting to be really nice work in language that shows these things, where you're basically using a rich model of the stimuli to extract structure and showing that this structure maps to the brain. Doesn't mean that your rich model of the stimuli is exactly what the brain does. It means that it's extracting similar structure. Did I answer your question? Okay, now I can show you what we can do when we have this. Here we have a model of brain activity that is a model that works well on a wide range of different images. This is being thrown on thousands of natural images, and it works well. So then we can start extrapolating from this model, and we can start putting images in the model that have never been in our database. And so we can start, for instance, putting images with wedges, okay? And we can start looking at the brain response as modeled by our model to wedges. And we can do a standard retinotopic analysis on this. So it's a retinotopic analysis, not on the brain data, but on the model. And so we can start getting then retinotopic maps of our model. And they work reasonably well. So what I like about this is that we've trained our model in natural images, and then we're showing that it works well for images that have quite different properties. Okay, so basically our model is slightly larger, slightly broader than the paradigm that we've used to train it. And we can also do this and create a face versus place opposition. And when we do this, we show that we're somewhat capturing the right regions. So our model predicts that some regions respond more to faces than pictures of houses. And so just for the fun, we did this by putting the stimuli of the AXB experiment in our model. And it's important to see that those stimuli actually have different, I'm showing them here, have different low-level properties than the images in our database. These are images of our database. These are the stimuli. And if you look at vision science, traditionally vision science tries to really control very well the low-level properties of the stimuli. And it's not always clear if results carry over if you don't do that. What I'm showing you here is that results do carry over if you don't do that. And I personally think that this is really exciting. I personally think that, in this paper I'm talking about, the one by Michael Eichenberg, the really interesting thing is that we've shown a model that is larger than the paradigm of the experiment on which it was trained, and that is, we're showing that it's not sensitive to experimental details. And for me, from an inference standpoint in cognitive neuroimaging, I think that's something important. I don't know if it's visible from the paper. Maybe we didn't write the paper well. Okay? So this is really what I'm personally excited about in this. It's what I'm excited about in this experiment, and I'd like to claim that this is something that can be achieved in general with encoding models. The things that encoding models give us is that because they can take larger descriptions, like more complex descriptions of the stimuli than standard models, standard GLM, they can model all aspects of the stimuli and not focus on whether this is a face or a house. And as a result, they can more generalize, and this can be tested explicitly, unlike most analytic model used. And the other thing is they require you to do less arbitrary choices in the way you describe your experiment. And hence you're less bound to a small set of hypotheses that is bound to your theory of the mind that you're trying to put forward. So I'm fairly enthusiastic about those models. All right, any questions on this? Yeah?
So just to clarify, the point is not that your model is directly predicting the activity in your brain, but rather it's learning features from the data?
Yeah.
Different hierarchies.
Yeah.
And then that information that is distilled through the network that does predict on a separate post-analysis. Does predict.
So here we have, if we think of machine learning, we have two steps. The first step is learning a good model of the stimuli. And this is done on data without brain activity. The reason this is done on data without brain activity is because we need heaps of data, heaps and heaps and heaps of data. And then the model is on different data. We have a different model that goes from, so this is like a stimuli to stimuli model, okay? So it's images to description of what's in the image, okay? So that's standard computer vision. Then, in another machine learning step, we go from stimuli to brain. And there we use the information that was extracted by the first step, okay? Does that make sense?
So that's a two-step approach.
Yeah, it is a two-step approach, yeah.
Not like altogether.
No, because we don't have enough brain data. If we had, it'd be interesting, but we don't, right? And also something maybe I didn't mention is that the whole methodology relies a lot on cross-validation for model comparison. I mean, we can claim that this model is a good one because we have compared it to other models that were either simpler or more biophysically, or thought as more biophysically plausible. And we're saying, it explains the data better. Now, this fraction of explained variance is in itself, I don't find a very interesting measure. It should be large enough so that we know that we're not capturing noise, but we're looking at fMRI, and fMRI is not only neural activity. So good to crank this thing up. I believe in explaining better the data. I strongly believe in explaining better the data, but it's not the only thing. We need to try to understand in the model what drives this link, okay?
Does it matter how many layers the network has?
So once again, I'll answer, I don't know because we didn't play a lot with this, but I don't think so. It might make your understanding more challenging. So the modern networks that have gazillion of layers, what you'll find is you won't be able to get a clean map like this, because you're gonna be distributing this information over 100 layers, and so basically you're gonna have noise on which layer predicts best. But then if you sample these 100 layers and you took 5 evenly distributed, then I'm pretty sure you'd get a similar image. But I haven't done it, so that's a bet.
And what are your hypotheses about the mapping between the image recomposition and the neural data?
So we're using a ridge regression, so we're using a linear mapping.
Why linear?
Because if you look at the shape of the data, so you have a few thousand observations and a few, I don't remember, but significantly more intermediate representations, so hidden units of your network. So you can't really expect a complex nonlinear model to work well, okay? From a machine learning perspective, if I have significantly more features and sample, I'm expecting simple models to work better than complex models. So that's a first thing, and that's testable via cross-validation. The problem is that this is time-consuming because we're fitting one model per voxel, and we're cross-validating it each time. So we're talking hundreds of thousands of fits, maybe more. So we didn't, try too many things. So that's the first reason. It's a machine learning reason, is stick to simpler models. Another reason is I don't want things too complicated to happen between my representation and my brain data, because I have things too complicated and I can't say that there's a simple link between the two, right? So in theory, well, more than theory, in theory, the data that's in here is a function, is a nonlinear function that is the data that is in here, okay? So if I'm allowing myself to have any class of function rich enough, then basically I can, if I had enough brain data, I could simply learn this transformation like this, okay? And so then my predictor would work very, very well to go from here to here, simply because it's learned nonlinearity, okay? So that's an argument that you'll find often to use linear encoding models. And I think there's some truth there. Either you want to use linear encoding models, or you want to use encoding models where you can open the black box and you can say, well, it has learned this function and this is what it captures.
What would those look like? The latter.
Sorry?
The second models, what would those look like?
People have used things like general additive models, and so that's kind of nice because basically you get a polynomial, and in certain cases it's definitely useful. I guess it's going to be case specific, but I would like my model to be able to relate it to some form of mechanism, even though if it's not biophysical, but some form of mechanism some form of plausible transformation in the stimuli. Any other question? If not, I'll move on to decoding models. So decoding models are really doing the converse. Okay? And why might we be interested in decoding models? Well, there's several of them. But if I've shown you that I can explain well the brain activity in a specific area by the presence of a face, is that telling us that this area is specific to faces? No. We have a logical fallacy here. We have one implication, stimuli contains face, implies activity in this region, the converse is not, we have no evidence for the converse, right? It's a standard logical fallacy. A good example is that if I say that all dogs eat meat, I eat meat, hence I am a dog. Well, said like this, it sounds stupid, but that doesn't prevent people from calling this area the fusiform face area. We need maybe a bit more evidence, okay? So this is a well-known problem in cognitive neuroimaging, is that we often would like to have evidence on what is the function of a given brain module, but what a given experiment tells us is really what is the neural support of a given function. And these are two different things. And it's easy to forget the difference. And the challenge is that in standard brain mapping, we're really manipulating the stimuli or the task, and we're recording the response, okay? So we kind of have the causal link in the wrong way. And that's just the way brain mapping works, at least in human fMRI. If you're recording mice, then it's different because you can start letting them do their own decision, and then you can start accumulating data on this. But in the scanner, with our standard experiments, it's a bit hard to do this. Not impossible, but hard. So really the way brain mapping works is that it accumulates responses to task, and then it crafts contrasts to isolate effects, or it uses an encoding model, which is a more sophisticated way of crafting contrast. Okay? So really, it's really first getting the impact, the simple impact of a task, and then trying to cancel for other aspects of the stimuli. And this cancellation is what people use to try to recover some form of specificity. And then they claim that there's a face-specific area, but it's really conditional to the experiment that people have done. Okay, so there is another way to look at this, which is to say, can we predict aspects of the stimuli given brain activity? All right? And this is somewhat inversing the standard approach that people are using. It's now, if you give me brain activity, I'd like to conclude something on the stimuli. And this is closer to the statements on what is the neural support of a given function. Okay? So basically predicting stimuli from brain activity, which is known as decoding. Now there's one caveat, is the way we run the experiments, this prediction is often done in a very closed world setting. We shown face and place. We showed that we can predict from a region that the subject is seeing a face rather than a place. If we jump to the conclusion that this is a face-specific area, our conclusion is wrong. It's an area that is more specific to faces than places, but we've only shown a very small number of stimuli, of conditions. So really the challenge to address here is that we need to show many different stimuli, many different tasks to be able to come up to a general conclusion, right? So then what people have been doing, and this has been pioneered by Russ Poldrack in 2009, is to use decoding across many studies. And if they reliably find a brain region that supports decoding for a specific aspect of a stimuli across many different studies, then maybe they can claim that this brain region is specific to this aspect of the stimuli. Okay? So So I'll come back to this, but this is a bit of a motivation for why are we going to do decoding. This is how I think about decoding. It's not the only way of thinking about decoding, but this is how I think about decoding. All right? And then we might want to go back to not only prediction, but also finding information on what brain regions support this prediction. And it's the same thing as the answer to the question that someone asked of why not use complex predictive models. And we're going to use linear predictive models, so linear decoders. The reason being that what a linear decoder really learn is a set of coefficients that will link brain activity to stimuli, and this set of coefficients is a brain map in itself. Okay? So if you think about what the linear model is, it's really learning a pattern, a set of weights on the brain that link brain activity to the stimuli. So with this, maybe we can start saying that we've recovered brain regions that are related, that predict the stimuli. Okay? So we can do this, and we can apply this, say, to a prediction of faces versus houses, and we can use the tool that's the favorite one in Neuroimaging, which is the support vector machine. And if we do this, we get an error of 26%, and we get this brain map. Okay? So we can use a different model. We can use, say, a sparse model. And then we use we get an error of 19%, and we get this brain map, right? Can you see it? Here we've got those dots here and those dots here. Or we can use a ridge, and we get 15%, and we get this brain map. So which model should I prefer? Is there an obvious answer to this question or not? I don't know. Seriously. No? Nobody wants to? I don't know. I mean, from a purely data perspective, I should prefer the model that has the smallest error. It's the model that explains best the data, where the data is, the stimuli conditionally on the brain imaging, right? It seems reasonable. I mean, the evidence is that this model is performing better. Do you agree with me or not? Do you dislike this model for a reason or not? I mean, I personally, yeah.
So it could be that this has low error, but your data is noisy, right?
Yeah, that's the case of any experimental data, right?
So you're tuning into noise, partially.
Yeah, but that's the case of any experimental data. So either I did my cross-validation right, so I need to try to do what I can about the noise, but at the end of the day, my results are always going to be conditional on the data and its noise. Right? I'm a bit uneasy about this point of view, because it's we've got a family of models. I'm going to pick the one that I prefer because it's more interpretable, where interpretable is something that has absolutely no definition. I've been working in this field for a long time, and interpretable means it gives something that is closer to what I expect. But I've been working in this field for 10 years, and in my experience talking to people, is interpretable boils down to it gives something that I expect. Because there's no formal definition, it is something that can be twisted in any way, and it is a magic term to say, I like this result better. And there's no way you can put any form of rigorous control on interpretability, unless we choose a working definition, but that's not what people do. I'm not happy, by the way, just to be clear. I'm very unhappy by this map. Extremely unhappy by this map. I'll also explain you why this is the case. But I find that what people are doing, which is saying, oh God, this map is ugly, I'm just going to use this one, I prefer it, is scientific. I'm going to claim it's scientific fraud. I mean, because it's just you got 3 models, one performs better than the other, one performs the worst. You prefer the results of the one that performs the worst. You pick this one.
Non-face areas also have some information on faces. Therefore, you could hypothesize that the previous literature focuses on the areas that are to lower the faces than other areas that are stimuli. But this is capturing areas that are non-face areas that have some information, maybe edges specific to faces and not to other stimuli.
Yeah, that would be a very valid hypothesis, and it's somewhat the theme that's underlying the original publication by Jim Axby. So it would, yeah. So basically, we could either come up with the story or just say well, the data is more complex than what we thought, and at the end of the day, being a statistician, I also have a statistical explanation to this, and I'll go through this. But the first thing I want to say is that at least in my opinion, we need to formalize these things a bit more than just interpretability, because I've had endless discussions with people, and there's no way around this, basically, because we could have priors, we could be Bayesian and have priors and say, well, from a Bayesian perspective, this is more likely. So this would be feasible. It'd be interesting. It's a bit challenging because you need to build those priors in an explicit way. Because what we really have here is an implicit prior, and we're looking at this and we're saying, based on what I know about the brain, on my studies and my review of the literature, this doesn't look quite right. And so this is an implicit prior. We could be doing this. It'd be really interesting. Well, I mean, the measure of in this experiment, the measure of human behavior that we have is only what people had been seeing. So maybe that's, in terms of experimental design, it's often good to get, some form of feedback on what the user, the subject is doing, to be able to maybe have, people do this a lot where they have basically 2 aspects of the task, one in which they use to control that the subject is paying good attention, and the other one in which they're really asking their cognitive questions. So that would be one way of doing things, but in this experiment we don't. And by the way, I don't want to bash this experiment because it's data that is better than most data that I've looked at by a significant margin. And the reason is that it has more repetitions. Yeah, sure.
Yeah, you said you didn't like this map. Why didn't you like this map?
That's a good point.
Okay.
Yeah, totally. Because it doesn't fit my biases. But I have no legitimate reason not to like it. It's just prejudice. I'm biased against this map. Okay, well, let me formalize this a bit, because this is actually a challenging problem from a statistical standpoint, okay? So really, from a statistical standpoint, what we're doing here is a form of inverse problem, where we are trying to find a map that predicts well, that minimizes best a prediction error. But this map is a high-dimensional object. It might have 500 voxels that we need to fit. It might have 5,000 or 50,000 if we're doing brain-wide. And we have a small number of repetitions. We might have 200 repetitions. You're already showing a lot of information to your subject. Your subject is exhausted, you can't do too much, okay? So in such a situation, this is an ill-posed problem in the sense that I have 200 repetitions, I'm tuning 500 coefficients for 200 repetitions. I will have an infinite amount of maps that predict as well. There's nothing we can do about it. It's just impossible to solve this problem as such. And cross-validation does not solve the problem, right? I have an infinite amount of possible answers given my data. So all the decoders have an implicit prior that go with the decoder, and it's a prior that's usually done for good computational and statistical reason. And this is where we could, inject our knowledge of the brain. Okay, and so we could say, well, I really want to find information in the FFA, and then we could use a mask of the FFA, and that would solve the problem. And that people have done this, and it's not, meaningless. But what's really important to have in mind is that it's a nil-post problem. Because it is a nil-post problem, it will have variance that you can't control aside from injecting prior in there. It's just impossible. The experiment does not bring evidence. The experiment brings a limited amount of evidence, right? And what goes with this is it's actually easier to predict than to know which is the best map to predict. All right? So just to give a bit of understanding of the inner workings of the estimators, let me just describe how these sparse estimators work. These sparse estimators work by using a term. So basically the estimators, they minimize the cost function, where the cost function is a measure of the prediction error. And on top of this, and that's really important, they add another term that's an arbitrary term, that's a term that is used to serve as a prior, basically. And there's a wide literature on this of why this is important, and it's crucial, but I won't cover the details. And one thing that we can do is we can add a term that will try to enforce some form of sparsity on the maps. And then we need to have a balance between the sparsity of the map and how well we predict. And if we do this, so this is known as an L1 norm, and if we do this, we can have maps that look like this here, where the map is very sparse but still predict well. And why is that the case? Because it found the handful of voxels that predict well. Now, the danger is to have a map that is too sparse. And so what we've done is to say, well, on top of this, we'd like some form of spatial structure, because we're looking for basically spatial modules. And so we're adding this information, and this appears as a sparsity in the gradient, but it doesn't really matter, okay? And by the way, the data doesn't tell us that we need to add this information. This is just prior bias that we bring in. And we could argue forever on whether or not this is a good bias. And I've had these arguments, and the only good way to test whether it is or not a good bias would be to see if it predicts well on many experiments, not one, because one experiment does not bring enough information to answer. So if we do this, by the way, we get, I should have represented the prediction error. We get a model that predicts better and that has a map that is structured spatially, okay? And the fact that it has a map that is structured spatially is not surprising, because this is just the ingredient that we put in our model. It's circular. The fact that it predicts better is interesting. It's some weak evidence that maybe we were right, but it's just some weak evidence that maybe we were right, okay?
Can you explain how you got to that one? Is that like some sort of elastic theory?
This is, I don't have the cost function here. Well, this is a bit like this cost function, but on top of this, you need to add the L1 norm of the spatial derivative of the image, okay, which is known as total variation, okay? That's how you get there. We've worked, as a disclaimer, we've worked on this class of model for quite a while, and they're available in Nilearn, so we're going to play with them. And so we've gotten to the point where we're completely biased. We love them, and we spend many years on them, and then to understand how they work. And so I'm soon going to switch to the notebooks, because I've talked for a long time. I just want to stress here that the different decoders will give different regions. There's nothing we can do about it. We might have weak evidence that we want to prefer one to the other, but as I'll mention later, it's just weak evidence, because cross-validation is just like any statistical measure. It has error. So what we've done recently is that we studied another class of models. So the problem with TVL1, as you'll find out, is that it's slow. And what we found is that people didn't like slow models. So we went in a completely different approach. And the approach, I won't cover it in detail because it's not available in Nilearn yet. But it's based on the idea of ensembling. So ensembling is when you learn many, many models on data that you perturb. So for instance, you randomly forget samples. You learn many, many models, and then you average them. What we like about this is that it gives things that are extremely stable to perturbation of the data by construction. And we think this is an important feature of data processing. Anyhow, this is one work that we did last year, but in the process, because I'd gotten more and more skeptical about our own work, in the process we also tried models on a dozen different experiments. Not one, but a dozen different experiments. And what I'm showing you here is each dot is a cross-validation fold. Each color is a different experiment. And what I'm showing you here is overall the difference in prediction score across many, many models. And so I think this gives evidence on what kind of model we should predict. Because across many experiments, we're testing our priors. We're testing which prior is one that generalizes best. So what we're seeing is that TVL1 actually isn't obviously better than an elastic net, so the new model tends to be better. Okay, and then we've looked at other things. We've looked at things like stability of the weights, and here we can see that, for instance, stability of the weights of the elastic net is abysmal. So then maybe in terms of interpreting weight maps, we shouldn't be interpreting weight maps of elastic net because they're very unstable. And maybe we should rather be interpreting weight maps of TVL1 or of the new model. And you can see that the new model is much more stable, but the reason it's much more stable is that it was built via this ensembling technique. I don't want to oversell this new model because we don't have it. You can't use it yet. Because it takes a lot of time to go from a paper to something that I can put in your hands and that will almost never break. And yeah, computational time is also important. And you can see here that TVL1 is quite expensive, okay? So, let's do some code and let's just try this out. So if you go to the hub, you'll find a notebook. I think it's called 01 something. Well, I'm going to do it right now. And basically, if you follow the notebook, and I'll follow it with you, it will run an analysis with an SVM on the phase versus place contrast of the Axby experiment. Then what I'll want is to redo this analysis with a sparse model and a ridge, so basically redo those figures, and then we can try TVL1 on this, okay? And this is interesting for two reasons. One is that you get a natural feeling of these things, and if you're fast, then you can start looking at what happens when you perturb the data, how stable are your results, and the other thing is you're also learning how to use Nilearn as we go, okay? So let's go to the hub, and let me share my screen now.
I should say if you're not using the hub, you should upgrade to a pre-release version.
Yeah, you don't actually have to. You're just going to be missing some of the interactive views. Most of the almost everything can be done with the latest Nilearn. So I released an alpha on Saturday to get some of the fancy new features, but you don't have to use it. Any reasonably recent version of Nilearn will.
Just type the code.
Yeah, so basically if I, to install an alpha will let me rather show how to get the information.
The hub has this alpha release, but if you're running this on your laptop, you'll need to run, maybe I'll just type it in general. I'll type what you need to type.
Right, that's a good idea. Why am I not getting? Looks like my Firefox died.
Install the pre-release version that we just released on Saturday.
Right, exactly.
That's the additional visualization tools.
You can also get this, I'm not sure why, but my mouse is not working on this page. But if you click to what's new, which is here, then you'll get the instruction, but I can't. Computers never work. Well, that's,
Me.
what's that?
It is a link for me just to
Yeah, no, it's just the mouse is not working on this page. I don't know why. I can't click on anything on this page. Is it the case everywhere? Oh, yeah. Well, I can
put the
yeah, if you can put, I'll just see if it works in Chromium. Yep, and then I can click here. Oh, it's my mouse that's not working in general. Ah, I've lost my mouse. That's going to be problematic. Does anyone have an external mouse that I could borrow? I tend to use my mouse very little, but for the Jupyter I'll need it, I think. Thank you, Kirsty. Thank you very much. So maybe this will work. It's on. So, no. Well, the good news is you can go ahead and go to the hub and start working. Sorry? A PowerPoint? Oh, a pop-up that's asking for my attention. Maybe. Possibly. I have too many windows as always. I'll kill my slides first. Well, I have to clean up my windows. Yay, working. Okay, great. Okay, so that was the line of code that we were talking about to install the pre-release, but it's not really important, okay? And the hub is here. And do I need to log off and log on to get the
notebooks, yes.
Okay.
So it's in hub at the top. No, not there.
Nope.
So that won't work. But if you see at the menu at the top, there's an item hub, and log out. That logs you out, and then click on that, and that should get you the.
Great, thank you. And so are people seeing the Nilearn? So I'm not, okay.
Let me do this for you.
Or I can do it on my local computer. Well, in the interest of time, I'll just do my local computer. So it's going to be slightly different than what you have, but okay. Oh, I lost my, and there we go. Okay. Okay, so first thing I do is I do matplotlib inline to capture the figures. And then second thing I'll do is I'll just retrieve the data. So we have in Nilearn the data sets, we have a bunch of data set fetchers, and they basically download data from internet. So if you run this, it's going to download data from internet, and then it's going to grab the functional data for the first subject. So it's basically a 4D Nifty file, right? Is everybody familiar with Nifty files? Okay. And then we can grab a mask of the eventual temporal stream, and we can plot it using Nilearn.plotting. And the important thing is that this data is not in template space. So when we're plotting it, we need to use the background image of the corresponding subject. Okay? And dim equals -1 is to undim the background, because on a video projector, you wouldn't see it elsewhere. Right? So this is the mask that we're going to work on. It was established by JMaxB using between us an overfit by selecting the data, the interesting voxels on the whole data set. But we won't worry about this right now. And then what we can do is that we can extract the data on the mask. And for this, we're going to use the Nifty masker. And what this guy does is it takes 4D Nifty images, it applies a mask to it, and it returns a 2D array that's made of voxel times number volume, okay? So it runs, and we can see here that we're giving it the mask, and we're telling it to standardize the time series. And when it has run, it returns an array that I call fMRI masked. So you see we're doing fit and transform on the data. So basically this is transforming the data. And this data is of shape 1452 by 464. Any idea what this shape means? So what's this array? It's 2D array. Sorry?
Could you do in 4 again?
Could I, what?
What does fMRI mask do?
What does fMRI mask? That is the data that's extracted on the mask. Okay? So it's a 2D array of the data that's extracted on the mask. Okay? Well, it's related to my question here. It's a 2D array. It has 2 dimensions. And the first dimension is the number volume. The second dimension is the voxel in the mask. Okay, so we have the data. We can see it 2 ways. We can see it as 464 time series, which is the time series of each voxel. Or we can see it as 1,500 feature vectors that are each time is the activation on the mask, okay? And what the Nifty masker does is it goes from the 4D image to this 2D data, and it's useful because it can apply a bunch of pre-processing, like spatial transformations or filtering. It's basically, we do a lot of simple data preparation steps in there, okay? The Nifty masker is also really, the role of the Nifty masker is to go from fMRI, or rather MR, or brain imaging data, to a feature matrix that's an abstract one that can be fed in scikit-learn. So we go from domain-specific data to general data. That's why it's there. And it's underlying many things. Even when you don't see it in Nilearn, it's hidden everywhere, because it's always useful to do this transformation. And it has a transform, and we'll see later that it has an inverse transform that allows you to go back to Nifty space. Okay? It's a key abstraction of Nilearn. Right? So that was the easy thing. The harder thing is that we need to load a description of the experiment And this is stored in a CSV file that is shipped with the data. And it's called CSV, but it's actually separated by spaces. So we need we're going to use pandas to load it, and we need to tell pandas that the separator is spaces. So we load the behavioral data, and we see two things. We see labels, and this is basically labels that describe the behavior. So it's what kind of object people were looking at. So scissors, faces, cats. And another column that is chunks, and it's the word that the people who've shipped the data have used to denote the block. Because this was an experiment with 12 blocks. Okay, block or session. Okay? So what we're going to do is that we're going to recover the condition ID. So we're just going to grab the condition ID. And it's now just a 1D vector of condition ID. And there are many different objects that were presented to the user, and we're going to restrict our analysis to houses and faces. Okay? So here we're just going to create a mask that is true only if the data is in house and face, not cat. Won't change much. A cat is a specific face. Yes?
Question. So the ones that say like scissors, is each one a different trial, or is each one just like a different time frame?
It's a very, very, very good question. In this specific experiment, it's per actually it's per volume, TR, okay? So here, this experiment is described per TR. And this is somewhat of a specific case. It's not a general case. In your experiments, if you're acquiring data, you probably need to get one response per trial, in which case you need to run a first level analysis with what's known as a beta series regression, which is that you're going to build a design matrix that models each trial independently, which is sometimes not possible because they're overlapping, but in this case doing decoding on this is challenging. This needs to be done with a different tool than Nilearn, and for this you could use NiStats, which is a standard analysis tool in Python, and which is probably going to get merged into Nilearn in the next year or so. And one of the reasons is that, as I was mentioning, there's no opposition between machine learning and standard analysis, and we find that we need this same set of tools, like building a design matrix. So I can't show you, like right now with Nilearn, how to do a beta series regression and decoding on it, because I don't have the design matrix generation, but maybe next year.
As a follow-up to that question, did you ever have to shift the design matrix due to the hemodynamic response delay, or in your experience, does it not matter?
That's a very good question. Russ Poldrax hates it when you do it this way because he's like, there's a 2-second delay anyhow, so you should really shift. It doesn't make much of a difference, but it would be more correct. So ideally we should do it. I'm trying to keep the thing as simple as possible. This experiment is also a very specific one. It's well-delineated block of sustained stimuli. They are well separated. So it's kind of the simplest experiment. And maybe I can plug in that's one of the challenges that we have developing Nilearn is we develop Nilearn only on purely open data that can be shared and reshared and everything. And there's actually not much of it. So we're really constrained in terms of what kind of, what we can put in our documentation, because we have a paradigm that our documentation must run. This is what I'm doing here is basically adapted from our documentation. And our documentation must run and must be reproducible by everybody. So it's constraining a bit what we can do. But things are getting better. Any other questions? Okay, so we can go on. We can restrict the analysis to houses and faces. So there was a typo. There was houses and cats. but I changed it to faces. I don't think it will make a big difference. Okay, so what we're doing here is we're creating a mask and we're selecting only the condition, so a mask, a temporal mask this time, and we're selecting only the conditions we're interested in this temporal mask, okay? And then we have significantly less samples, right? Then we have 200 samples, because there was only 1/10 of each of the samples that were related to each condition, okay? And we shouldn't forget to apply the same mask to the target. That's where we're going to have a target vector that doesn't have the same dimension as our data vector, our data matrix, and scikit-learn is going to complain, rightfully. Okay? And then it's just a question of using scikit-learn, as you've already seen with the course by Jake. So we're just going to get support vector classifier from scikit-learn. We're going to be careful to use kernel equals linear. If you don't think it's a good idea, don't do this, and we'll cross-validate it. We'll see who gets the best predictive performance. I hope I will. Okay, so then we have our support vector classifier, and then we can just fit it to the data, okay? So we fit it to the pair of fMRI data and condition, and it runs. And then we can predict, and we're predicting faces and houses. And then we can look at the difference between prediction and the actual data, and no difference. We're really, really good. Did I do something wrong? Does this mean anything? Yeah, I didn't split the data. Okay, so I have no control on the model. This thing doesn't mean anything, okay? So what we can do is split the data, and we could fit on all the data but the last 30 time points. And then we can measure the error rate, and it's not as good, which is more meaningful, okay? You have to keep in mind that face versus place position is one of the easiest thing to do, but it's also good for a tutorial because I can have you work with simple models on a small amount of data. But it's really something really easy. If you like do this, if you analyze this data over and over and over again, you might train your eye to be able to look at the data and tell versus it's a face or a place. It's visible with your naked eye, which is not something common, but still good in terms of understanding what's going on. Okay. So then we can do this in maybe in a more principled way, which is cross-validation, right? So we split the data. So we repeatedly split the data by leaving out a fraction of the data, train, test, and redo this split many times, and then we get one prediction performance per train and test, okay? And then you can see here that I made a mistake. So I forgot to pass the CV parameter to my cross-validation function. So if I do this, I get 5 answers. And the reason I'm getting 5 answers is that I'm running a k-fold with 5 splits, okay? And my prediction performance oscillates between perfect prediction and say 97 prediction. And I can change things, and I'll get different results. Ooh, I get significantly different results, or maybe not significantly. Why am I saying this? I'm saying this because cross-validation results, like any other statistical estimate from the data, have a variance. They're not, there's noise in this result. So I'll come back to this, but don't trust those results too much, right? I'm perturbing stupid thing that shouldn't make any difference, and I'm getting some difference. Okay? So this is showing me that there is error there. Okay? So maybe the best way, by the way, to do this cross-validation would be to leave one block out. Because the experiment has a natural structure, and what we'd like to learn is really something that generalizes to a new block. What we really don't want to learn is something that generalizes to the next TR, because generalizing to the next TR is somewhat trivial. Okay? So for this, I can use a leave one group out, and in terms of groups, I'm giving it this session label. Okay? In which case I'm going to get how many answers? Oh God, this is bad. I'm going to get 12 answers because there were 12 blocks. And I find this really bad because I get 100% prediction accuracy, which is really telling me that this is too easy. Maybe I should have kept the house versus cat. It's slightly less easy because we're so tuned to faces. The humans are so tuned to human faces that we get a massive response to them, and it's really the simplest thing we can do. So maybe the cat was a better idea. Okay, and then I can look at model weights, and for this I can retrieve the coefficients of the SVM, and I get a set of coefficients that are of which dimensionality? 1 times 464. What does 464 mean? It's the number of voxels in our mask. Okay, so I get basically 1 weight per voxel. And I can turn it back to a nifty image by using the inverse transform. And now I'm going from a vector of weights to a nifty image. Okay? So you can see here that the nifty masker is really going from nifty to matrices and vice versa. So I can turn it back to an image, a brain image, and once I have a brain image, I can either save it to disk using its toFileName method, or I can plot it using Nilearn plotting. And this is what it looks like. The good news is it's well focal on the ventral temporal cortex. But that shouldn't be a surprise because this is the mask that we used. Okay? And this mask was actually extracted from the same data with the statistical analysis on the same data, which means it's actually biasing, it's actually a circular analysis.
And if it's multi-class, you just get coefficients for each boundary.
Yeah, that's exactly it. And you could run the whole thing without the restriction to 2 classes. I'm just like making things easier so that they run faster. So there's an exercise, but we're going to take the break.
Just a quick question. Can you put the scale of those weights in context, or what's the expected rate?
No, it'd be kind of hard to put this scale in context because, I mean, it's feasible because if you look at the expression that you have a linear model. Your y is basically minus 1 and 1. And so the scale has mathematical meaning, but not the one that maybe you'd like to have. And this could go on to how do we test significance on this? And this is a horrible question. This is a question in which people have a lot of naive, good views. Oh, I just need to permute. I just need to. But it is a difficult statistical question because I don't want to go too much in this detail, but for 2 reasons. One of them is that this model is a conditional model where you're learning the response of one voxel conditioning on all the others. So now the null hypothesis of this guy is slightly more complex and slightly more structured. And the other reason why it's horrible is that, as I mentioned, this model is ill-conditioned. So anyhow, this feature map is all over the place. Change a bit your data, it's going to be all over the place, right? So it's a question I'm very interested in, and we have a lot of work on it, but I don't want to cover it because it'd take a while. Okay? So we had an exercise, but we're going to take the break, which is to change a bit the analysis that you're doing using, for instance, different decoders. And during the break, you can leave running, because this is going to take longer, you can leave running the analysis using SpaceNet. If you want to look at the code, you'll find that it's actually simpler because SpaceNet embeds a nifty masker inside itself, because SpaceNet is, so SpaceNet does TVL1 and other spatial priors, and it's a model that is adapted to fMRI, so it's a model that really does more clever things, okay? So you can just run this and look at the code if you're interested and ask me questions, okay? And maybe we can debrief this after the break, okay? Maybe I'll take questions after the break, But yeah, feel free to interrupt me during the break and ask me questions also. All right, thank you. I could use a decoder on 2 different regions and then compare the prediction accuracy on those 2 different regions. How does that compare with what I presented you? Well, that's completely part of the framework. It makes sense. And the question then is, how do you compare prediction accuracies? And I'll talk a bit about this. Are there any other questions on what I talked about? Okay. Why would you want to compare across participants?
When or why?
Why exactly?
So is it possible to, so these are all individual single subject local things? Is it possible to go to group level maps? And then if that's the case, then you would need to be able to scale everyone in a similar way, right?
Right. So I guess there are different points of view on this. The traditional point of view is decoding captures very fine information, and this fine information may not carry across participants. So you do your decoding model in a given, in a given participant. That's the traditional point of view. I tend not to believe in it most often. I'd say that most often. So for me, the reason why decoding does not generalize across participants most often is simply because there is some form of overfit. We've learned something that was specific we've learned some form of noise, and it's just a regularization problem. And so if we're able to have a good decoder, it should generalize across participants, at least on some tasks. Because I don't believe that if you do a phase versus house, it's a coarse-grained information that should generalize. And many, many times we've pulled the data across participant and we've done, say, cross-validation, leaving one participant out. So it's like a stronger generalization, and it works. Now, for certain tasks, it might not because the information is fine-grained, but my conjecture is that it would be more often the case that they generalize across participant than not. And I know I'm in severe disagreement with some people in the field, and I just think that we need better empirical evidence of one or the other. Does that answer the question?
How do you take into account univariate effects, or do you just not care, which is also a legitimate approach to say that univariate is just a form of multivariate?
So there is a bit of a confused usage of words in the community. People called standard analysis univariate, but it's not. We've stopped doing standard analysis univariate in the 90s, and we do general linear model. So it's multivariate. It's just multivariate on the behavior side and not on the brain side. So the first thing, this mass univariate, I think, is an extremely confusing term. The real difference between decoding and standard analysis is the direction of the inference. Standard analysis, so the two differences. One is you worry about out of sample properties, you worry about prediction, and you do cross-validation. But that's more of a methodological aspect rather than a modeling aspect. From the modeling aspect, it's really which way you're doing the inference. So standard analysis, mass univariate, is univariate in the brain direction and is an encoding model. And we're doing decoding models.
I'm talking more, if it was maybe that just
Okay.
I'm talking more about mean activity in region first.
Oh, some people do things where they remove the mean activity of a region. Yeah, I know this. I don't know why they do this. I mean, I've read the papers, and it's just not the way I use this tool, so I can't really answer. But yeah. Yeah, because I mean, I know why they do this. It's because they want to show that there is no univariate. And once again, I'll say I don't think it's a good choice of word. I think the good choice of word is marginal versus conditional link. You have, the question is, are you interested in the link between a given voxel, a given functional unit, and the behavior marginally on all the others, so forgetting all the others, or conditionally on all the others? If you're doing univariate, you're doing marginal. If you're doing decoding, you're doing, well, on most but not all models, you're doing conditional. Because you're learning a linear model where you're conditioning on the others. So this marginal versus conditional is an interesting question. I'd rather frame it this way than univariate versus multivariate. And maybe for this, there's really a good paper by the group of Moritz van Troep, Grosse van Troep, it touches, so Moritz Grosse van Troep, it's a good paper in the last few years, and it touches on causality because, where is it? He publishes a lot. Somewhere in there. So he touches on causality. Oh, this one. No. This is an opinion paper that didn't go through. But you can still look at the opinion paper that didn't go through, and you can look at the citations, because the real question that we would like to get at is the causal question. Brain activity causes versus as a consequence of the stimuli / the task. It's a very difficult question because we don't have intervention. If we had intervention, if we could go and kick neurons out, then we'd have the answer. We don't have the intervention, so we're really trying to do some statistical evidence of causal direction. In which case, it's really useful to think about what evidence do I have conditionally on what, and they have a good paper discussing this. It's going to go a bit too far for this course. Any other questions? But to be clear, I think these are very interesting questions, and I would like the tools that we have to be used to answer those questions, rather than let's do a search across the brain and find that this region is activated in a searchlight analysis. But they're also harder questions to ask. We don't have canned answer. Okay, so the analysis using SpaceNet ran, at least on my computer. I don't know if it ran on the hub. Was I doing cats versus face? No, I was not. Okay, and so this is the kind of brain maps that it estimated. So you can see here that they're actually weakly spatially structured. They're not strongly spatially structured. And the reason this is the case is that the SpaceNet object actually tunes all its hyperparameters on the data. And so here it puts very little prior, because the data, this is a simple task. The data is high SNR, so the object doesn't need to put much prior. So if you were doing if you were doing, for instance, a cat versus face contrast, the cat versus face is one of the hardest because the brain responds quite similarly to cats and faces. And then the SpaceNet object would put a lot of prior, and you'd have very smooth map. Okay. So we can look at it this way, and the other way we can look at it with the latest Nilearn release is, so if you run the notebook, at the end we're using the ViewStat map. So by the way, did this work on the hub? Are you getting this interactive viewer or not? Yes, cool, great. This is new. Like we did this last month, and this is the first release. I'm really happy to see that it's working for people. Okay, so. And this is the map that we're getting, and once again, we shouldn't over-interpret it for all kind of reasons, but still, we can see that it's capturing information in the ventral temporal stream. Here we also get in the, I don't remember the name of this region, but it's a region that is also known to be related to face recognition. So we're getting a fairly interesting map of regions that are related to a phase versus place of position. Okay? So the tool runs. How to interpret it is between us really not always easy. There are all kind of reasons why we could get these maps. For instance, the subject was nodding on the right when there were faces and nodding on the left when there were houses. But I mean, this goes beyond the course. So any questions on this specific? Nope. So then I'd like to switch back to the slides, if I can find them. Yeah, here. I'd like to switch back to the slides, and I'd just like to talk a bit about cross-validation. So really, everything that we're doing is based on the idea that we're going to test which model is the correct one based on cross-validation, because it's the reason we do this is that given that we're using models that are not simple statistical model in which we can do a controlled analysis of every aspect of the model, we can't easily have statistical control on those models. I mean, it's extremely hard. And it's also possibly brittle, because we could have hypotheses that are not valid for the data. The nice thing about cross-validation is that it's a non-parametric test, and just tells us whether the model explains well the data, yes or not. Now, it has also a certain amount of variance. I showed you that if I change the cross-validation object, I get different answers. Here, what I'm showing you is, so it's in a different setting, but it's still cross-validation and brain imaging. Here what I'm showing you is a competition where there was money involved. That was not set up by me. It was trying to predict whether patients had schizophrenia or not. And there were two test sets. There was one which was a public test set where people could see their scores, and there was one which was a private test set where people could not see their scores. And they could see their scores in the public test set, but really at the end of the day, they would get money if they scored well on the private test set. So it's the idea that you need to generalize to unseen data. So people really have an incentive of doing as well as possible in the private test set, even though they don't have it. What I'm plotting you here is the difference between public and private test set. The difference that I can know only because the competition is over and the results have been published. They couldn't see this during the competition. Okay? I personally, I mean, when I first did these things, I found it striking to see the width of this distribution. It's plus and minus 15%. It's huge. You know, if you get a 2% increase in prediction accuracy, you might be happy. I might be happy. But clearly, we don't control things to plus and minus 15%. Why is this? Any idea? So, okay, I'll tell you. The two test sets were of size 30 and 28. Tal, you had?
Well, actually, a question, actually, but I think it's
sample size. So, you know, let us consider our decoder as something that flips a coin. You know, the probability of getting it right given the data has some form of randomness because there's noise in the data, and this randomness is coin flipping. Ideally, it's not a balanced coin flipping. It's not 50-50. Ideally, are classified as better than 50-50. So it's a biased coin. So what I'm telling you is that a biased coin is a binomial distribution. It's a simple distribution. So what I have here is a binomial distribution of degrees of freedom 30. It's like I'm flipping the coin 30 times and I'm averaging the result. Now, I can plot this binomial distribution. It's a simple mathematical object as a function of the sample size. And these are the plots I'm showing you. So basically, a binomial distribution with n equals 30 is fat. It's very, very, very broad. And this width goes down as the number of samples increases, as 1 over square root of n, just like any width in statistic. And so the point I'm trying to make here is that your typical your typical sample size is in the 100 or 200. So then your width of the measure that you're getting with cross-validation is on the order of, say, 10%. Okay? And there's nothing you can do about it. Just nothing, because that's a best case scenario. That's just, the randomness related to the test set. You could have randomness related to the train set. You could have adversarial behavior where the train set doesn't match the test set. And in practice, we do observe, width that are slightly broader. Okay? So really the point here is if you have 100 samples, you know your prediction accuracy only with a delta of plus and minus 10%. And so, by the way, between us, this is something I hadn't realized for many years. And at some point, I clicked, and then I started getting very skeptical of everything we were doing, and I just started doing much more experiments on our methods development. And there's nothing you can do about this. Absolutely nothing you can do about this. And a graph that I don't have, I should have put it here, is that I did a meta-analysis of published prediction accuracy for different questions, for different pathologies, as a function of sample sizes. And what you're seeing is that basically the larger the sample, the smaller the prediction accuracy that people report in their papers. So there are two explanations possible for this. The one that many people prefer is that, larger sample sizes are more heterogeneous, hence it's harder to predict in them. I'll show you, I don't believe this because we have evidence it's not the case, even for horrible pathologies that are extremely heterogeneous. So my personal hypothesis is just that when we analyze data, we try things out. I do like everybody else. We try to smooth the data with a smoothing of 6 millimeter, 5 millimeter. We tried SpaceNet, SVM, and we report what works best, because it works best. But we're just exploring this randomness. So, it's a form of p-hacking. I don't like the word p-hacking because it implies that people are dishonest. You might not even be dishonest. You might just be trying things out and you don't realize, okay? But you're really exploring this randomness. And if you report the best, then the best is pretty much, if you have 100 samples, is pretty much 10% away from the true. If you have 30 samples, it's 20% away. If you have 1,000 samples, it's 3% away. Okay? So this is how I explain the fact that if you have larger samples, you tend to have smaller prediction accuracy because you have less wiggle room. Okay? So this is really to stress that cross-validation is not a magic bullet. I really believe in it, by the way, and I don't think there is any other answer to this question, but at some point the data is limited. It can only tell you a limited amount of things. Okay? So it's kind of contradicting what I said earlier, which is to say the name of the game is to predict. Well, if my model predicts better, then it's a better model. I was answering a question to Satra, who's, I believe, not in the room now. But so yes, but you take this with a grain of salt, and you know what kind of confidence you have in your prediction, and you don't conclude if two models are in the confidence bounds, or you take the one that you prefer because of your prior information, as long as they're not statistically different. Okay? Any question on this?
fluke or what's really the
The fact that the first, well, no, I don't think it's a fluke, and we just ran, I should update the graphs to have the results of our latest competition. We just ran a competition with a larger sample size. There was 2,000 subjects, 1,000 in the test set, and it's almost the same result. It's almost the first model that predicts. Not exactly. People outperform our baseline, but not very much. The reason is human overfit. People are tweaking their model to make it perform better. As they're tweaking their model to make it perform better, I mean, that's a competition. That's what you want to do. As they're tweaking their model to make it perform better, they're overfitting.
Oh, I see. So basically, because the first draft was like, oh, this is just showing you what you can do.
It's simple.
Human regularization.
It is a human regularization. Yeah. And I'm not, I don't want to make fun of people because they do this mistake, because we participated in the PAC competition on depression, and we thought, we're the best machine learner on earth. We're just going to win this competition, and we're not going to fall in this trap. Bang. We did. So it's really hard. There's no, and I talked to people after this competition, because there are graphs in the competition that show you that as a function of time, people overfit more and more and more. So as a function of time, they're getting better on the data set that they have and worse on the data set where they should. And how do you avoid this? Well, ideally, the more data you have, the less you have this effect. But with 1,000 subjects, you still have. So ideally, you have an inner model of what is a complex statistical model and what is a simpler one. And this comes from the statistical literature, basically. And you should, take the one that performs best, but penalized in a non-formal way by its simplicity. And that's really something that people don't understand, by the way. It defeats the intuition. It really defeats the intuition, the amount of wiggle room you have, and the amount of overfit that you can get, even if you incentivize people. And in our competition, the winner got 3,000 euros. That's a fair amount of money. So the incentive were not at all to overfit. And there was 1,000 data points. So you think, we're not going to overfit. And people still overfit. And even us, when we did this, we still overfit. So it's just like, maybe the answer to this is we should have only a very small number of models that are considered as good one, and we should not stray away from them. And anybody who wants to introduce a new model, like what people do in my team, we spend our life introducing new model, should test it on many, 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 many different data sets and show that there's a consistent gain on many, many, many different data sets. But pretty much nobody does this. Does that answer your question?
Yeah, it's fascinating.
It's in a sense, it's bad news, especially for methods developer like me. But the good news is that if we manage, to find this trade-off in complexity, then we can have a model that we can just give to people, and ideally it works. Okay? So I've talked about, this setting to go from brain image to behavior or pathology, and before I've talked about this setting, so encoding to go from behavior to brain image. And this is interesting because it can help decomposing brain activity, decomposing the behavior into different representations of the stimuli that may be relevant for the brain. And now I would like to talk about resting state analysis. So shift gears a bit. And the reason why this is important is that data without labels is cheaper to acquire, but also is universal. And I think that's something that's quite important in terms of resting state. Resting state is reasonably universal. Task is not at all. People disagree on the way you should run a simple task. And so in practice, so I'm not a cognitive psychologist by training, so I don't even have an opinion on what is the best way to run the task for a given problem. All I know is that as an observer, I see that this is not converging and that the community is not able to establish standard tasks. Whereas REST fMRI, which is a much poorer recording in terms of cognition, is something universal, and people are piling up, well, somewhat universal, and people are piling up data, right? So we just get more data of lesser quality. So, talk a bit about REST fMRI. And for me, REST fMRI is interesting for what we call population imaging. And the idea is that these days we're starting to get huge amounts of subjects with REST fMRI. We're really looking at the 10,000, soon 100,000 subjects with REST fMRI. And from a data perspective, this is a much, much richer data set. So we can start learning structure in this. And really the challenge that we have here is, can we ground intersubject psychology or psychiatry, so things like personality psychology or psychiatric disorders, on brain measurements? This is the research agenda. In my opinion, there are other research agenda in resting state, but that's the one I'm excited about. And that really requires looking at the difference across subjects. The challenge that we face with resting state is that there is no salient feature in resting state. This is a typical resting state data. Basically, it's structured brain noise. So you need a pipeline of extracting information from it. And there's a pipeline these days that's somewhat universal that works as following. First, you define regions. Now, that it's better to define functional regions, but you can also define anatomical regions. Then you learn interactions between those regions, and we might call this a functional connectome, but it's basically something that captures interactions at rest across region. And then you can detect differences across conditions or across subjects. I'm saying across conditions because there's been very beautiful work that showed that things like perceptual training has an impact on the structure of activity at rest. And so this is good evidence to show us that the structure of activity at rest is related to the abilities of a subject, okay? And this is very well controlled experiment. So our typical pipeline for resting state data analysis is this one. So defining regions, extracting time series, building a functional connectivity matrix. So importantly, a graph in mathematics, this is called a graph. So some people call this a network. They're similar words, well, words that denote similar concepts. So a graph and a matrix are the same thing. They're just two different representations of the same thing, right? A square matrix and a graph, same object, okay? And so then on this matrix, on this functional connectivity matrix that we could call a functional connectome, then we do intersubject analysis using supervised learning, using an SVM, using whatever we want, okay? And so what I'll cover in the following half hour is this pipeline. And not supervised learning, because to get information we would need many subjects, and many subjects entails large computational costs. And so this is really starting to work, more and more. We're really starting to get predictions of non-trivial things like autism status or lifestyle from brain activity at rest. So there are many ways we could be defining functional regions, and one of them is to use clustering. So the simplest clustering tool that we could use is the k-means clustering. It's good because it's very fast, at least the implementation in scikit-learn that we use in Nilearn. It's limited because it has no spatial models, so the solution for this is just to smooth the data. By the way, this is a universal solution in fMRI. Smoothing the data always improves the result. It's not completely true, but there is some truth there. Another approach is to use the word agglomerative clustering. The nice thing here is that it's very easy to add a spatial constraint here. I should say that those two models are exposed in a parcellation object in Nilearn. So it's very simple to use in Nilearn, but I won't cover this in the notebook. And there's another class of model, which is to say that instead of clustering, so basically a clustering is a hard assignment. I'm putting each voxel in a region. And this is a bit of a simplifying model, and more likely at the group level, voxels have a certain probability of belonging to a region or another. The signal is basically mixed. And one way of modeling this is basically to say that we're going to take the data, which is a number of voxels by number of time points, and then we're going to decompose it in a product of a small number of time series and a small number of spatial maps. And this is a matrix factorization problem that can be instantiated in many, many ways. And it's been instantiated many times with ICA. What ICA does in this problem is it seeks independence between the maps. So you're basically trying to find maps that are independent and explain well the data. And another way of instantiating this is to use sparse dictionary learning. So basically the idea is that you seek sparse maps. And this is, for instance, the result of what you get when you do sparse dictionary learning. So you're basically finding a set of brain regions that are in a sparse background that explain well the signal. By the way, this is interesting because this is really a result of a dictionary learning on 40 subjects resting state data, and one of the maps looks like this. And this is really, a set of structures that are things that are the gray nuclei of the brain that we know well. And so that's not surprising because this resting state activity is structured by the underlying structures, brain structures, right? So that's exactly what we're finding when we're doing a linear decomposition, okay? And you can see the benefit of sparsity is that there's a small number of structures that explain the signal. Yeah?
So far many parcellation being proposed, and I think that each year there's more.
Sure. We have a paper that we're going to submit real soon.
Yeah, so because using some well-known parcellation is good because we can compare results from previous studies. And what do you think, we should rather use this like well-known parcellation or use like data-driven parcellation?
Well, I think this should be an empirical question first, and I'll provide some evidence. And then there's two problems. And then we're going to get in sociology of research, is that the well-known parcellations are well-known because they were done by someone who was powerful. And I'm going to take a specific example. The AAL atlas is outrageous. It looks like nothing. And there's a reason. It was done early on by manually delimiting regions on a single subject. But it's the parcellation that's most used to do resting state analysis. It's ridiculous. It has no sense. So here we have a clear failure because it is true that there's really value of using the same parcellation than everybody. There's clear value because then you can more easily communicate your result. But if for this we need to use something that is meaningless, it's unsatisfactory. So I think what we should do is, as a community, find a way of concluding on what is a good parcellation, and this should be established independently by a group of experts, and then maybe separately people should test parcellations. But what we have currently is we have people publishing parcellations in Nature because they're funded by the largest projects in the US, and the reason why the parcellation is the best is pretty much because it's been done by these guys, and these guys know the brain really well. And I think this is somewhat of a failure of scientific inference. Now we're going to have to be pragmatic at some point and reduce the number of parcellations. But this is a great way to transit to my slide, which is how do we ask this question? And so we've asked it in a specific way, that's maybe an imperfect way, is that we've looked at prediction. So we've looked at this pipeline across a bunch of different studies, and we varied the parcellation. And when I say we, it's really Kemalaka, who's sitting at the back of the room and really did this work. Kemalaka, do you want to, you're in? Kemalaka's over there, right. So he did this work, and you got to realize that it's extremely hard work because basically you're running a lot of predictive modeling, and what we did is we ran them in nested cross-validation with many cross-validation just to try to reduce the variance of cross-validation. And we couldn't test everything, and the paper got back where the reviewer is basically telling us you need to test more things, but basically we're limited by computing power. But we tested a bunch of different things. We tested well-known parcellations that tend to be structural, but not all of them. So this is the Yale and this is the Harvard-Oxford. These are structural parcellations. We tested functional atlas. This is the power atlas, and this is the Basque atlas that was done by Pierre Bellec. And I have my opinions on these, right? But this is unrelated to my opinions. This is the data. And we tested different clustering methods, and we tested different decomposition methods. And so I know what is my pet approach here. And my pet approach is basically dictionary learning. And it performed well, but not significantly different from RTA. So I'm disappointed, but that's life. And then in terms, of gradation, what we're seeing here is that the methods that use decomposition models, so linear decomposition models on the data, tend to perform better than the others. And in general, that the methods that tend to learn functional regions tend to perform better than the methods that are based on anatomical regions. And my conclusion on this side is twofold. Either you don't care about using a standard parcellation and you have lots of computing power, in which case you could use group ICA or dictionary learning, or you'd rather stick to something that is published and also make your life much, much easier because you don't have to play with those complex tools. And then I would say that you should rather use the Basque atlas, but the power one would work well also. Okay? And from a more meta perspective, it's basically you want parcellations that are learned from fMRI data rather than from the anatomy. And this is, the bowl is probably open. And what you're seeing, by the way, is that the variance of this is large. And goes back to the fact that the variance of method validation is always going to be large. I would like it to be more work in this direction, by the way. But it's very hard because there are no simple stories. Nothing just works uniformly well. And if you want to do this with a nested cross validation, it becomes very computationally expensive. And we could even test my pet model, which is called multi-subject dictionary learning, which is a model I think is really elegant. It's just too costly. The reviewer also said this. You should test multi-subject dictionary learning. Yes, I'd love it, but we can't afford it. So that's one thing. That's parcellations. And then the other thing I want to talk about is which parameterization of functional connectivity should we use? And maybe the most natural one is correlation matrices. And this is a real data set where we have 3 controls and 1 subject that has a stroke, a fairly large stroke. And what you're seeing is that the differences are extremely non-local. They're extremely distributed, both across the controls and in the patient. And so it's extremely hard to do statistics on things where the differences are distributed across many, many coefficients. It's just, you won't get, a simple story there. You can look at partial correlation matrices, because partial correlations make more sense because they capture conditional relationships. And then the problem is that they're noisy because they're hard to estimate, okay? So, once you're there, you're stuck, because basically, we did this a while ago, and we thought, okay, we need some way of describing this from the statistical perspective. I won't walk you through the math because it's fairly heavy math. If you're a statistician, this is related to information geometry. What information geometry does is it tells you how multivariate objects that are estimated from the data vary under null hypothesis, basically. It's a well-grounded theory, but it uses tools from differential geometry and tools from statistics. But basically, it's actually fairly easy to use information geometry on covariance matrices, and we can have a description of the variations of covariance matrices under the null, and then we can use this to reparameterize the covariance matrices. So to do a nonlinear transformation of the covariance matrix in a new matrix that under the null hypothesis varies in a IID white way. So this is what I'm showing you here. And what you're seeing is exactly what I told you, which is that for the control, we just have white noise. We have unstructured noise here for the control. But for the patients, we have clear differences, okay? So this is work that we did a while ago, and it was very hard for me to try to convince people on this because it was based on difficult mathematical arguments, and that just doesn't fly in this community, for good or bad reasons, but I'm not going to blame people. I mean, the question really is this sophistication useful for anything, or are you just mathematicians that are playing with concepts? So we put this aside. A few years later comes the problem of predicting from connectomes on large data sets. Then we can pick up this problem again and we can instantiate it and we can see if it makes a difference. We can test a different parameterization. This is the same paper by Kamalakar, and what you're seeing is that tangent space parameterization tends to give better prediction overall. So this is independent evidence that is orthogonal to our assumptions that is telling us that it's probably a good tool to use for population imaging in resting state. Okay? It's also slightly more involved. So it's available in Nilearn and you're welcome to use it or not. But there are good reasons why maybe it's a good idea to use it. With that, we have a bit of time left, and I'd like to switch to notebooks. Any questions on this, by the way? No? You're all tired?
I have a question. What would be the expected behavior of reviewers of your paper when you make some of these decisions? I'm thinking about the Atlas choices. What would be the expected behavior, and then what would be the sort of behavior that you would ideally like them to
Well, okay, that's an interesting question, because I would naturally reply to the second one, and then I'm going to try to twist my mind and find all the kind of horrible things that a reviewer could tell you. Well, the review could tell you, could you please use my pet parcellation because I'm last or first author on that paper and I just want citations. That could happen. The reviewer could tell you, well, I don't believe what you've done, but I believe this famous paper that's well cited, you should try it. Fine. That second comment is actually maybe valid, honestly. Don't explore weird things. I get the same thing. If somebody uses something I never heard about, I'm wondering, did this people p-hack that answer? And this is also one of the reasons why I put the tangent space on the side, is like, nobody's using it. I mean, it's going to become p-hacking. And now that we've got larger data sets, I can convince myself that it's something that's valid. But for me, it goes back to it's the same question than the parcellations is, we need to agree on a subset of things that we explore that are valid things, but this should be done not only on based on fame of the last author. So and honestly, I think the community is in general willing to do this. It can happen. It's hard, by the way. It's really hard work. But and then what I would like to see, it's a trade-off as a reviewer. You don't want to be overly picky, and you don't want to like pick on every little detail. So if the choice seems a sane one, I won't argue. Unless I'm very dubious about the results and I really believe that people p-hacked, in which case I might suggest, this is really cool, can you also do this other confirmatory analysis? Reviewing is hard. Any other questions? No? So you want to wake up with a little notebook? So let's switch to the hub. And let's switch to the resting state connectome. I added a notebook that I won't cover, which is Nilearn 101, but I'm just leaving it for you. It's a very simple notebook. If you got confused about things, maybe it will help you understand things about Nilearn. Okay, let's switch to and I'm going to kill my decoding notebook so that it doesn't use resources. So, what we're going to do here is that we're going to look at region extraction. We're going to look basically at the first step of the connectome pipeline, and we're going to do this on an open data set of ADHD patients. So we're going to fetch 20 subjects of rest data. So here you're immediately seeing the challenge of resting state data analysis is that we're starting to manipulate larger data sets. We have to. And then what we can do is that we can apply dictionary learning because it's my pet method, but maybe if you want, you can apply ICA, or you could even apply parcellation objects. And so we're using dictionary learning, and I'm going to ask for a very small number of components because it's easier to look at results. And I'm going to smooth because things just always work better when you smooth. Okay, I'm a bit tongue-in-cheek here. The guiding principle for choosing the width at which you smooth is that this conditions the size of the structures that you're going to recover. And if I want to be pedantic, I could say this is just an instance of the match filter theorem. It's signal processing that tells me that the best filter to recover a certain signal is the exact shape of this signal, okay? So if I smooth by 6 millimeter, I should not be surprised that everything I find is bigger than 6 millimeter. Okay, so it's really a trade-off. It's a bias variance trade-off. If I don't smooth, I'll find maybe noisier things, but with more details. My experience also is that with the more data you have, the less smoothing you need. And these days we're working on terabytes of data and we're not smoothing at all, but that requires terabytes of data. So here what we're doing, this is going to take a wee while, is that we're running dictionary learning on those 20 subjects, and it's learning those spatial maps that we call component images. And so it runs, and we're retrieving those component images here, okay? And then I've asked for 5 components, and so then this component image is a 4D image with 5 networks in it. And I can plot it like this. Oh, that already ran. That was fast. Oh, I know why it ran. It ran because I put the memory. So this thing does caching. So it uses disk space to not rerun when you're giving the same arguments, okay? So this is great because it allows you to iterate faster, and it will blow up your disk. So then you need to remove the corresponding folder. Okay, then we can look at the maps that were estimated using ProbAtlas. What ProbAtlas will do is it will plot the outline of each map, basically. So what you can see here is that the dictionary learning has basically divided up the brain in a small number of networks. And if you know brain functional architecture well, then maybe you'll recognize the yellow network. What network is the yellow network? It's the default mode network, right? And so one thing, by the way, is that the order, there's a bit of randomness in those networks. The reason it's a statistical problem. What we're doing is we're doing a problem that is even more ill-posed than supervised learning. And so there's a bit of arbitrary in the answer. So when you run this on your computer, you're going to get a slightly different answer from what I get. And one of the things that will be different is the order of the map. That's completely random. So technically it means that the default mode network will maybe not be in yellow, but maybe in red or blue or green, okay? So what we can do then is show each map. And to show each map, we're going to iterate across this image. So we're going to use iter image, which allows us to iterate, to take a 4D image and iterate on each of these. And then we're going to plot each image. So we can do this here. So we should get 5 plots, right? There are 5 components. We should get 5 plots. So we're getting our 5 plots. One of them is the default mode network. And here you have a visual network. Here you have something that looks like an auditory network. Here you have something that looks like noise. This is basically CSF noise. And this is not surprising because we're looking at resting state data. This is an API sequence. It will capture much more than neural spiking, okay? We should expect to see this in our data. And this is another network. So this is a very crude decomposition. I've asked for only 5. Yeah? It's an interesting question. There are really 2 points of view on this. We could try to denoise our data, and it's going to be imperfect denoising. So we could try to minimize the amount of confounding that we have. There are several ways we could do this. We could, for instance, regress out movement, or we could just throw this in the ICA or the dictionary learning and hope that it separates the corresponding networks. There are 2 points of view there. I tend to prefer using the ICA or the dictionary learning to separate things out, because the denoising is always going to be imperfect, and you can try denoising and you'll still find those components. So the way we tend to work in the lab is we post hoc identify components and reject them. And so FSL fix, for instance, works like this too.
Yes, but if you first remove denoise, then you may end up with different ICA components.
You're telling me my results are partly arbitrary? My answer is yes. Deal with it. We have 20 subjects. We're trying to learn brain structure from 20 subjects, 5 minutes, they're sitting in the scanner not doing anything. It's a bit of a miracle that we're finding this. So really what will happen is that if you start having 2,000 subjects, the results will be less arbitrary. They'll be a bit arbitrary, but less. So I tend to prefer to work in very large data sets these days. But they're going to be a bit less arbitrary, but there are good reasons to say that it's an ill-post problem even with 2,000. And supervised learning is by construction ill-post. Because it's non-convex cost functions, because you can change things without changing the cost function. So supervised learning will be a bit of arbitrary anyhow. So I don't like to over-interpret the ICA maps. I like to interpret them, but not the nitty little details about them. Especially what I really hate is when people take 2 groups of subjects, run ICA in group A, run ICA in group B, and tell you, ooh, things are different. For mathematical reason, you've run 2 non-convex models on which you've shared no information, they fall in different local minima, and you're telling me that things are different. What's your statistical control on that? So what I like, my vision, and it's not the only vision, but it's somewhat shared by many people, is ICA or dictionary learning is a partly arbitrary data reduction, not fully arbitrary because it's finding things in the data that make sense, but it's partly arbitrary. It's a partly arbitrary data reduction. And after this, I will use this to build a connectome matrix. And on this, I'll do a statistical test. Ideally, I should be able to do this many, many times, perturbing the seed, and find similar results, where similar is going to be in the eye of the beholder. Or we could put metrics on this, but it's going to take us a long, long way. People have done this. And there's a package that does this for ICA that's known as ICASO. I think it's beautiful work. It's also extremely consuming. And by the results that I'm showing you, showing that ICA is better or not than dictionary learning, are done running it many, 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 many times on perturbed data. This is why it's very expensive, but this is why I trust the answer. Okay? So once we have this, one thing that we can do is that one thing that Nilearn can do is that it can break these network in different regions. So if we look at the default mode network, we might be interested in breaking it in subregions, because if we think in terms of components, then we might want to capture the interactions between those subregions. And as a disclaimer, if you put your number of components to be much higher, this is less necessary, because as you increase the number of components, networks tend to break down in subregions. Not completely, but they tend to break down. And in our methods comparison, we haven't found empirical evidence that this was useful, There's no strong empirical evidence that this was useful. I like it because I found that the results are more interpretable, but then we can go back to my rant about interpretability. It's basically my personal bias. Okay? So my personal bias is that it's good to break the networks down in regions. I have no evidence for it. Feel free to do it differently. And Steve Smith and I disagree there. I think we'll continue disagreeing because I was not able to bring in evidence. So we can use the region extractor to do this. So the region extractor, what it will do is it will break the regions in subregions and it will extract the time series on each subregion, okay? So when we fit it, basically we're breaking down, so we're giving it those components, and when we fit it, we're breaking down in regions, and then we get those different regions. And then we can visualize the results, and the plot looks quite similar, except that now each region in the network is broken down in a different component, right? So now I have different colors across the regions of the default mode network, okay? And now I have 26 regions instead of 5 components. Those are all very arbitrary numbers. There's no true 7 networks that underlie brain function. What I could also do is I could plot all of these regions. So there's one map per region, and it's a continuous map, right? It's not a 0 or 1 map. So this takes a little longer to run. And then what I can do finally is that I can extract the time series on each region, and I can build a connectome from this. So these are my maps, by the way. So we can see the different subregions. We can, this is part of the default mode network. This is another part of the default mode network. This is yet another. So we've broken down the brain in subregions based on functional data. And so then we can extract the time series on each subregion. And for this, I'm using extractor.transform. And by the way, here, I am putting in the information that I got from my pre-processing, which is the time courses of movement. Because here I feel it's useful to, it's not only I feel, I can show you it's useful to remove them from the signal. Okay, so basically, when I extract the time series, I remove the confounds. I orthogonalize the time series with the confounds. This is, by the way, something, this specific notebook that I'm showing you is specific to ICA or dictionary learning, but it would actually be much simpler if I just said, I'm just going to use the atlas because it's pre-computed, and I just need to use some form of nifty masker to extract the time series. It would be much simpler, much less computationally expensive, and maybe you should do this, or maybe not. I don't know. You make your choice. But where I'll have an opinion is that you should always remove the confounding signals that are related, for instance, to movement, or if you have some heartbeat information or things like this, okay? And if you don't, I'm not showing this in the notebook, but if you don't, you'll basically lose the structure of brain activity. Question? So it's simultaneously. It's important. So technically, I think, but that's something that should change, by the way. I think technically what we have is that, so you need to do it simultaneously, for instance, because suppose I'm doing a low-pass filtering, and I do it before I remove the confounds. So I low-pass filter, and then I remove the heartbeat. Heartbeat is a high-frequency signal, so then basically my resulting signal still has heartbeats. So I seem to remember that the way we do it is that we apply those filters both to the signal and the confounds, and then we remove the confounds. The goal being to be orthogonal to the whole subspace. The I would really like to have another option, which is to use a cosine basis for the, so we're using a Butterworth filter. I'd really like to have the option to use a cosine basis, because then your cosine basis appears as a specific set of confounds. And then you're doing only one step. And this is useful for irregularly grid data or missing data when you've got spikes or things like this. Okay? This is something to be done. And this makes me think, one of the reasons, for instance, that we don't apply filtering running the ICA is that if you filter, then it's going to be much harder to separate the noise components from the non-noise components. So it's really, you've got 2 points of view. Either you think you have pre-processing that can make your data very clean, in which case you do this, and then that's once and for all you're removing confounds. I personally prefer to run ICA on data on which I haven't tried to make it fully clean, get it to separate the signals and then remove them afterwards. But we haven't run a very strong empirical study on this. The FSL people have, even though they're using a slightly different pipeline than we are. So this is code that's a bit complex because, and maybe it could be simplified. Yes, it could be simplified. God, maybe we should do this as a project. But we're extracting on those 20 subjects. We're extracting time series on every 20 subjects. Then we're creating the correlation matrix we're using for this connectome measure, which is something that can compute correlation matrices, partial correlation matrices, tangent space embedding. And then we're averaging these, okay? And here so this takes a little while because it needs to run on all the subjects. And then we can plot this correlation matrix as a matrix. And you'll have to trust me that it gives this result. And what you're seeing is that it's a very structured matrix. It's got blocks. Do you have an idea why this is the case? Actually, do you have an idea of how many blocks there are? 5. 5 is a magic number. It's the number of components that we've asked for. So when we broke down those networks tended to be more correlated. So it's really the structure that we're observing. I have a bias, after having looked at brain correlation structure in many different ways, that brain correlation structure is overall structured in blocks, but not only in blocks, also blocks with bridges. And this, from a network modeling perspective, this is a community structure. So I'm not the only one to have this bias. It's a very common hypothesis. So this bias makes me like a matrix like this because it has a well-pronounced connectivity structure. So it's still running. So I can then display this matrix as a connectome. And for this, I will need to extract coordinates that basically represent, well, each region, which is something I can do reasonably well at the region level, but not at the network level. And so I do this using this function, find probabilistic atlas cut chords, which was added, by the way, in the latest Nilearn release. So if you have the version before, you don't have this. And then I can use plot connectome to plot this. And here I have a beautiful connectome. What I find quite amazing about this connectome is that it's purely learned from the data on 20 subjects, and this is actually not high quality data. This is not, HCP quality data. And it still is capturing a lot of things that we know about the connectome. Let me just rather look at the interactive plotting because it's easier to understand. So this is also new in the latest Nilearn. And so what you can see here, so some people call these objects hairballs. And there is a point. I mean, they're really hard to understand, and we shouldn't over-interpret them. But what we can see is that there is some form of triangular structure here in blue and in red, so in positive and negative correlations. And this triangular structure, it goes from the PCC, with the parietal cortex and the ACC. Any idea what this is? This is the default mode network. Okay, and so it's a strong structure. We also have strong frontoparietal links. So these are all features that are well known well-known features of functional connectivity. Okay. So we shouldn't overinterpret this. This is just, one method applied on 20 subjects of fairly noisy data. What we should do is apply this on more data, more, 100 of subjects, and see what's stable, what's not. Maybe change some aspects of the methods and see what's stable and what's not. This conclusion on stability is going to be more of a qualitative conclusion unless we put specific metrics on this, which is possible but is a bit of work. And ideally what we should do is then try to correlate how this structure varies across subjects with some description of the phenotype of the subject, or try to predict the phenotype of the subject from this structure, which I won't do. And the reason being that in the data set that we're using here, this link between phenotype and resting state data is a very weak link. And I found that demoing methods on the very weak link is not a good thing, or maybe it is a good thing, but just to show how arbitrary methods are, because we just don't find something that's very robust. And so maybe I can plug in a project that I would find that would be absolutely fantastic to do next week, which is to find an openly available data set that can be shared, which is very restricted, where you have a certain amount of subjects, not too many, because if the data sets are too big, I can't do a tutorial on it because I drown the infrastructures, and on which we can predict a phenotype. And based on our work on functional connectivity, I found that the phenotype that was easiest to predict was the age of the subject. If you have an age band from 20 to 60 years, that's a large age span. So it's not surprising that it's easy to predict, right? So if we can build an example that works on already pre-processed data and shows that the various pipelines work to predict age, it'd be a really cool project, I think. And with this, I'm over time, so I'll end up there. If you want to continue as an exercise later, you can vary, you can use ICA, you can change the number of regions. It's just easy, you can just run this. Any questions? Everybody's tired and hungry? Well, I'll be around to answer questions.
Thanks.
Thank you.